Welcome. In this video, we are going to look at some inverse functions and their derivatives. Recall that in a previous video, we have seen that the function f of x equals x squared has an inverse function, which is the square root of x, if we restrict the domain of f to the set of non-negative real numbers. Now, looking at the function f of x equals sine of x, the question that we want to start with here is it possible to restrict the domain of the sine function in order to define an inverse function for it? Because as it is, the sine function does not have an inverse function if we do not restrict its domain. For instance, take the value y equals 1/2. If we try to find two angles where the sine is equal to 1/2, we would at least have two possible values, pi over 6, 5 pi over 6, but there would also be other values that are not illustrated here on this graph. So there are actually infinitely many possible values where the sine of x is equal to 1/2. So what we need to do is restrict the domain of sine so that this question, the question being which angle is the sine of that angle equals to a given value of y, we want that question to have a unique possible answer. Now, to recap what we just said, the graph of y equals sine of x is that of sine, and at the moment x is allowed to be any real number. If we invert y and x, we get that x equals sine of y should be the graph of its inverse, but we have a problem. The problem is that if we solve x equals sine of y, we won't get a function in the sense that for a given value of x, there are many possible values of y where x equals sine of y. And one of the example we considered in the previous slide is 1/2 equals sine of y, and we saw that there are many values of y, many angles where the sine is equal to 1/2. In order to define an inverse function for the sine function, we need to restrict its domain to an interval where the equation x equals sine of y has only one solution for any given x in the range of the sine function, which is from -1 to 1. In other words, if we go back to this curve here, given a value of x, which is represented along the y-axis here, okay, it's the other way around, because when we're considering the inverse function, we're changing x and y. So looking at the inverse function now, the x values, they lie on the y-axis of the sine curve. So given a value of x, for example, of 1/2, since this horizontal line intersects the sine curve in many places, there are many solutions to the equation x equals sine of y. So we need to choose a portion of the sine curve where this won't happen, where any horizontal line between -1 and 1 won't intersect the graph of sine in more than one place. Furthermore, we want the equation to have a solution always for any value of x between -1 and 1. So we need to choose a portion of the curve that covers any value between -1 and 1 on this y-axis, and where any horizontal line will intersect it in only one place. Try to think which part of the curve would work out. Now, if you consider the part in blue, okay, you can see that it works. It goes from -1 to 1. So in fact, this point here is pi over 2 minus 1. And this is pi over 2, 1. So all the values of y are covered between -1 and 1. And at the same time, if I draw a horizontal line anywhere, it will intersect the part of the sine curve in blue in only one place. And this means that we need to restrict the domain of the sine function between -pi over 2 and pi over 2. So the angle we'll be looking for will be within that range. If we reflect the blue curve across the line y equals x, we will get the red curve, and it will be the graph of the inverse function, which we will call the arcsine function. So the arcsine function starts in -1 minus pi over 2 and ends at 1 pi over 2. So from our previous discussion, we get that given any x between -1 and 1, we call the arcsine of x the unique angle between minus pi over 2 and pi over 2 included, such that x equals sine of y. So let's look at some examples where we're going to compute the arcsine of a value between -1 and 1. Now, what's the arcsine of 1/2? So remember, the arcsine is an angle. So we're looking for an angle between minus pi over 2 and pi over 2, where the sine of that angle is 1/2. There should be a unique answer. Try to find it. Pi over 6. So the answer is pi over 6. Obviously, we're looking for an angle in the first quadrant because the sine represents the y-coordinate of the point on the unit circle, which belongs to the terminal side of the angle. So because the y-coordinate here being 1/2 is positive, that angle will be in the first quadrant. If the value would have been negative, if it would have been arcsine of -1/2, we'd have looked for an angle in the fourth quadrant, but a negative angle, and it would have been minus pi over 6. What's the arcsine of minus √3 over 2? Again, we're looking for an angle where the sine of that angle is minus √3 over 2, and where the angle is between minus pi over 2 and pi over 2. Try to think about it. It's minus pi over 3. Okay, fair enough. Now, what's the arcsine of sine of 3 pi over 2? Now, there's a little trap here because you may think, oh, arcsine and sine cancel out each other. They're inverse function of one each other, so the answer would be 3 pi over 2. However, remember, we're looking for an angle between minus pi over 2 and pi over 2, and 3 pi over 2 is not an angle in that interval. So we have to think about what the sine of 3 pi over 2 is in the first place. And it's -1, because at 3 pi over 2, the y-coordinate of the point is -1. So we're looking for an angle now where the sine is -1 between minus pi over 2 and pi over 2. So in this case, it is minus pi over 2. So it's not always the case that the arcsine of the sine of an angle gives back that same angle. Okay, it depends of the angle in the first place. So if it's between minus pi over 2 and pi over 2, it works out. For example, in the case where we're looking for the arcsine of sine of pi over 4, okay, now since pi over 4 is between minus pi over 2 and pi over 2, well, the answer is going to give back pi over 4. So in the first part of the video, we just looked at the definition of the arcsine function. Now I want to look at the derivative of this arcsine function. Basically, to find the derivative of any inverse function, you proceed in the following way. You take the equation of the original curve you have. So here we were working with a sine function, so it's y equals sine of x, and you invert x and y to get an equation of the inverse function. So in this case, the inverse function y follows the equation x equals sine of y. Afterwards, you take that equation, and we're looking for an expression for y prime, the derivative of the arcsine function represented by y. So what we're going to do is differentiate on both sides to get some derivatives showing up. So if we differentiate with respect to x on both sides, I get dx of x is the same as the dx of sine of y. Okay, because the two expressions here are equal, their derivatives are equal. This part here is easy to differentiate because we're differentiating with respect to the same variable that shows up here. So the derivative of x with respect to x is obviously 1. Now in this case, we're differentiating with respect to x a variable y that depends on x. So this is a function of x. So in other words, this is a composition of the sine function with a function of x. So to differentiate this, we need to use the chain rule. So on the left-hand side, the derivative is 1, and on that side, the derivative is cos of y times dy dx, which we will write as y prime for convenience. This is just the chain rule on the right-hand side. So if we solve for y prime, we get that y prime is 1 over cos of y. So we could stop here. In other words, we could compute the derivative of y prime by doing 1 over the cosine of y. So at a point xy on the curve of the arcsine function, we could compute its derivative by computing 1 over the cosine of the y coordinate. But actually we can do something better because we can replace this by an expression in terms of x. Because remember, this is the derivative of a function of x, so it would be nice if we can't have an expression here that's only in terms of x, if possible. It's not always possible, but in this case it is. What we do is we use the identity sine square of y plus cos square of y equals 1, and we solve for cos square. And if we do that, we get that cos square is 1 minus sine square, and therefore cos of y is the square root of that. Now you may say, well, hang on, if I solve for cos square, there would be two solutions, plus or minus the square root. But the cosine here is positive because the angles y we are looking for are between minus pi over 2 and pi over 2, and it happens that the cosine is positive for those angles. So it is legitimate to just use the positive square root here. So we get that the derivative is 1 over the square root of 1 minus sine square of y. And the beauty here in using this expression instead of this one is that sine square of y, well, is sine of y squared, and sine of y is actually x. So we can replace this by x squared. And there we have a formula. The derivative of arcsine of x is 1 over square root of 1 minus x squared, where x is between minus 1 and 1. And below is the chain rule version of that differentiation rule. Now, if we want to compute the derivative of the natural logarithm function, which is the inverse of the exponential function, then we take the equation for the exponential function, which is y equals e to the x, and we switch x and y in order to get an equation for the natural logarithm function. So we get x equals e to the y. And we proceed in the exact same way as we did with the arcsine function when we wanted to compute its derivative. We first differentiate on both sides with respect to x, because what we want to get eventually is an expression that involves dy dx, or y prime. So on the left-hand side, we get dx dx, which is, again, 1. On the left-hand side, we get ddx of e to the y being a function of x. We need to use the chain rule on the left-hand side to differentiate it, and we get e to the y times y prime. And on the left-hand side, the derivative is simply 1. Now we solve for y prime, so we get y prime is 1 over e to the y, and we could be happy with this formula, except that we can do even better here, because we can write an expression for the derivative in terms of x only. Remembering that e to the y, if you look at the first line, e to the y is equal to x. So this means that y prime is just 1 over x, and that's the derivative of the natural logarithm function. So we get another basic formula, which is that the derivative of the natural logarithm function, ln of x, is 1 over x. And below you have its chain rule version. What's interesting here to notice is that the derivative of a logarithm is not a logarithm. It's a rational function. And you can also think of the derivative we had for the arcsine function, and it's not a trig function, it's actually something else. It's not even a rational function because there's a square root in the denominator, but this is one of the first cases that we see where the derivative of a function doesn't give a function of the same family of functions. Thank you for watching.